Welcome to Chill Skills Sporlan Tech Talks. The topic for this episode is What is Refrigeration Part 2, which means we did a What is Refrigeration Part 1 earlier.
Part 1.
You can go back and listen to that on YouTube if you'd like. I recommend that. This one happens to be the 13th, if I recall correctly, in a series of presentations that deals with supermarket refrigeration. While it does not necessarily follow the old agenda of the supermarket seminars, it is an important aspect of refrigeration science. It's very applicable to the air conditioning side of things as well. Today, you'll learn why things become cool, cold, or frozen by transferring heat. Again, don't forget about part 1. Here's a shameless promotion for the next webinar. Why don't you tell us about it?
I can do that. So our next upcoming webinar will be October 22nd of this year, and we'll be talking further about methods of temperature control. We've already had, I believe, 2 webinars on that subject.
3.
And
you can't count unless you got your shoes off, right?
Oh, darn it. Yeah. That issue again. Well, at any rate, this one will be talking about EEVs controlling discharge air temperature. That's one of my favorite methods. But hey, I'm biased, so, you know.
Fair enough. Here are a few instructions. If the speaker on your computer doesn't work for you, you could simply dial in with your phone. There should be a phone number somewhere on the invitation, but in the case you've misplaced that, the number's here on the slide. As we move along and you have questions, you could type those into the Q&A window, and we'll answer most of those questions live if we can. A lot of times we run out of time to deal with that, and we'll post answers to all the questions online eventually. However, if you hang on, there's a good bet that we'll answer the question you have if you just listen to us during the course of the webinar itself. And just so you know, we are recording this webinar. Should we run into any broadcasting problems today, you can always go back and listen to the recorded version. It'll appear on Facebook Live to begin with for your listening pleasure, and then later on, because we got to do a little extra editing, on the Sporlan YouTube channel. Hello, I'm Jim Jansen, Senior Application Engineer for the Sporlan application team. That's me on the left. And joining me today is John Whithouse. John is the Sporlan Principal Engineer for our division. He's a published author, consultant, as I have said very many times in the past, all around extra smart guy. And that means John's a big deal around here, and we're excited to have him once again. Say hello to everyone, John.
Good afternoon, everyone.
I thought you were supposed to say hello. But...
Oh, I can say hello too.
Okay.
Or hello also.
Okay, fair enough. Fair enough.
So,
and just so everyone knows, we needed to give some thanks to our friend Gene Ziegler. He was one of our former teammates that helped us to put this presentation together, and he deserves some credit. So here's to you, Gene. And Phyllis is back in the room joining us today. She's our marketing, our communications director. She tells us what to do and when to do it. And every once in a while, we'll listen to her. And of course, we are all maintaining that safe 6-foot minimum clearance between everybody as we need to do. Now, John, I've always admired your mustache, so I thought I'd just steal it for a while. But that means you got to give it to me. What do you think?
I'm not sure that's a fair trade.
You don't like that. Huh? I have to say, John, you're one of my longest lived co-hosts, and I really do appreciate you joining us here. If you have any follow-up questions or feedback, you may contact us via the email, or you can contact Sporlan Tech Support Team directly at svdtechsupport@parker.com. You can always call our main number, which is 636 area code 239-1111. That's a general number for our headquarters. That gets access to things like customer service and tech support, and I'll show that information again. This graph is going to be a plot of water temperature versus that thing we called enthalpy in the last presentation. Enthalpy of water or heat content in BTUs per pound mass. Water boils at 212 degrees Fahrenheit at atmospheric pressure at sea level. And by definition, water at atmospheric pressure at any temperature below 212, as you can see there, is considered subcooled. And John, why talk about water at all?
Well, a good reason to talk about water is we're all very familiar with water. Our bodies are mostly water, actually. That's not really the point, though. But we're all familiar with water. We know how water freezes, but more importantly, how water boils. And I think most of us have an understanding of how pressure affects that boiling. And that goes a long ways toward helping understand what we're going to talk about today.
Perfect. Now, starting with a 42 degree F temperature here and beginning to transfer heat to it, assuming we are working with 1 pound of water for every BTU or British thermal unit that's added, a corresponding temperature increase of 1 degree Fahrenheit will be achieved. This is the definition for 1 BTU. As additional heat is added, eventually the water's temperature will increase to 212, as you can see here. This is the saturation temperature at atmospheric pressure. At this point, the water begins to change state from a liquid to a vapor or to boil. As noted on the graph, the water experiences no further temperature increase as long as the pressure remains constant. The water at saturation or boiling temperature has reached the highest temperature the mixture of liquid and vapor can ever achieve. Increasing the amount of heat transferred to the water simply increases the rate at which the water boils. The temperature of the saturated vapor will be 212 degrees. Notice that we've got the saturated condition there, and notice we've indicated the boiling condition, and notice that the latent heat of vaporization is shown to be 966.6 BTUs per pound. That's pretty important. What that indicates that water is a very efficient and valuable heat transfer mechanism. Once the vapor has separated from the liquid, additional heat transferred to it results in a temperature increase. And that puts it into the superheated range. And you can see here, if we're talking about 230 degrees, 32 degrees Fahrenheit above the 212, that's essentially 20 degrees of superheat.
Yep.
And forgive me, for those of you who are metrically inclined, this presentation will use, if I say this correctly, IP units versus SI.
Inch pound.
In the future, we could consider electing to use a different set of units, perhaps.
We could, absolutely.
Now, here, we're going to do a similar graph. This graph is going to plot temperature in enthalpy or heat content in BTUs per pound of the refrigerant that is known as R22. Now, you might say, why use R22 in this particular example? And I'd say it's because it's still in service in quite large numbers around the globe, many locations, and it has served as something as a baseline for such examples in the past. But like we are going to do probably a future version that has SI units, we'll probably do a future version that uses more friendly, environmentally friendly refrigerants.
Yes, we will.
All right.
We can certainly do that. But
Here,
to the same point we talked about with water a while ago, R22 is something that's very familiar to many of us. So
Absolutely.
it serves as a good substance to talk about for this type of exercise.
In the area on the left side of the graph, the R22 is subcooled liquid. In the central part of the graph, it is boiling at saturation, just like the water. And in the area on the right side of the graph, it's being completely vaporized. So it's getting into the superheated vapor range. R22 at atmospheric pressure are 14.7, now wait for this, pounds per square inch absolute, reaches saturation or boiling temperature at negative 41.5 degrees Fahrenheit. Notice the latent heat of vaporization for R22, wait for it, is 100 BTUs per pound. As depicted in the previous two graphical examples, a boiling liquid will always absorb more heat than a vapor experiencing a temperature increase per unit of mass as a result of the change of state of the liquid as it goes from a liquid to a vapor.
That's correct. When we see that word latent, we're always talking about heat that goes into or comes out of a phase change, that does not go into change of temperature of that substance.
You can see here, if the refrigerant is continues to absorb heat to this level that we show here, just in this particular example, minus 21.5 as an increase from minus 41.5 is indeed a 20 degree superheat. And we're indicating those numbers here as I move on through the animation on this slide. Now, it's kind of interesting to look at a little bit of the history. And you know, John, this helps in some weird way to remind me of the debate that took place the other night. Many of you probably watched the presidential debate. You might have, John. I don't know if you did or not. But,
you know, now that you mention it, there is something a little bit, yeah.
But but what this brings to mind is, if we wanted to get through this presentation a little quicker, I could continue on from this slide. You could start about the midpoint, and we could just both read the slides simultaneously. We get through the whole thing quite a bit faster. What do you think?
That sounds effective.
But I don't know that everybody would appreciate that. So keep in mind that prior to the widespread availability of mechanical refrigeration, block ice was actually harvested from lakes, ponds, and rivers during the winter months. It was stored and delivered to be used as a means to move heat or to actually refrigerate. Quarries with openings that served that purpose and natural caves were sometimes used to store the harvested block ice. It would be packed in sawdust or straw as insulation to help preserve the ice into the warmer months of the year. Early refrigeration. Now, even as large industrial mechanical refrigeration systems capable of producing ice became increasingly commonplace, the daily delivery of block ice remained prevalent, particularly in larger communities. You know, there's always the whatever ice and fuel company. Well, they sold coal and oil and ice. They had a big central system that was in a location in the city that was, their sole purpose was to generate ice that got chopped into blocks. Block ice was then placed into an ice box in the home as a means to refrigerate and preserve fresh foods. And even to this day, well after mechanical domestic refrigerators became widely available, they're still oftentimes referred to as ice boxes. The term ton in the refrigeration industry corresponds to the use of ice as a means to refrigerate or move heat. The cooling produced by melting 1 ton of ice in a day is referred to as 1 ton of refrigeration. And it has been empirically determined and calculated that 288,000 BTUs per hour, or 288,000, BTUs, are required to melt 1 ton of ice in a 1-day period. And that's pretty interesting.
That's correct. And if we do the math, we get to that familiar 12,000 BTUs per hour equals 1 ton.
I'm glad you mentioned that. And here it is right here in front of us.
Slide.
You divide the 288,000 BTUs per day by 24 hours in a day, and we've got the 12,000 BTUs per hour. The capacity of air conditioning and refrigeration equipment is often expressed in terms of this unit, and its equivalency back to 1 ton correlates back to the use of ice. 12,000 BTUs per hour divided by that 60 minutes in an hour shows that it requires movement of 200 BTUs per minute to provide 1 ton of refrigeration. Depending upon whether you're air conditioning biased or refrigeration biased, you may have more experience using the 12,000 BTUs per hour rate or the 200 BTUs per minute rate. To continue with the flow rate calculation, divide the capacity by the change in enthalpy. This equals flow rate. This is just another way of saying heat transfer equals flow rate multiplied by the change in enthalpy. This all comes and is derived from the first law of thermodynamics in the conservation of mass for an open system. If you say it another way for the mechanical engineers in the audience, heat transfer, or Q dot, is equal to mass flow rate, M dot, multiplied by the change in enthalpy, or delta H. Now for a 1 ton system, capacity, or 200 BTUs per minute, divided by the enthalpy change, or heat content of the refrigerant used in BTUs per pound, will provide the flow rate in pounds per minute for a 1 ton system. The heat content of a refrigerant is designated, it's a new term we're going to define here, as the net refrigerating effect, or NRE. The NRE of a given refrigerant is specified at a known liquid temperature as it enters the expansion device, versus the temperature after the refrigerant has completely vaporized in the evaporator. For different applications, the NRE could be specified at different temperatures for use in comparing refrigerants. In this example, the NRE for some previously common refrigerants in BTUs per pound are listed. Note the liquid is entering the expansion device it's the fine print, at 90 degrees F and is being completely vaporized in the evaporator at 20 degrees F, with, of course, degrees F inferring degrees Fahrenheit. We talked all about that in the last webinar.
We did. And so that example would basically be probably representative more or less of something like a medium temp refrigeration system.
Absolutely.
Fresh food.
Now, again, net refrigerating effect, or NRE, is the amount of heat each pound of refrigerant absorbs from the refrigerated space as it changes phase from a liquid to a vapor in the evaporator. And again, we're talking about it in BTUs per pound, and it only makes sense if you define the boundary conditions.
Correct.
Here are two examples of using the formula to obtain flow rate. One for R22 with an NRE of 70 BTUs per pound, and another for R404A with an NRE of 52 BTUs per pound. Recall the 200 BTU per pound divided by NRE and BTU per pound equals the flow rate in pounds per minute.
Mm-hmm.
For R22, 200 BTUs per minute per ton divided by 70 BTU per pound equals 2.86 pounds per minute for that 1 ton system. If we look at 404A, a historically common refrigerant, 200 BTUs per minute per ton divided by the NRE, 52 BTUs per pound, equals 3.85 pounds per minute for that 1 ton system. Notice that the higher NRE for R22 yields a lower flow rate in pounds per minute for that 1 ton requirement.
Correct.
Does that mean, John, that the higher the NRE, the more efficient the refrigerant happens to be?
That can be an indication, but it's not necessarily. That's not necessarily so.
But it's part of the picture.
It is part of the picture. In that particular example, you do have to move more mass flow of the R404A than you do the R22. However, there are still good reasons to use the R404A.
Absolutely.
And it does not necessarily cost that much more to compress that amount of R404A versus that amount of R22.
Subject for us to talk about another time, I think.
It is.
The NRE, or heat content, for a few more recently introduced refrigerants are listed here. Well, some of them are not so recent. Take the R290, for instance. That's actually propane, and that's been around for a while. The heat content, or enthalpy ratings, have been derived at specific conditions, that is, with, in this particular case, 90 degrees Fahrenheit liquid entering the expansion device and 20 degree Fahrenheit saturated vapor exiting the evaporator for this particular example. Here's a graphical explanation of the NRE. The NRE for any refrigerant at specified saturated liquid and vapor conditions may be derived by using the thermodynamic information that may be depicted in a typograph that you see here, known as a pressure-enthalpy diagram. Now, some people might say, okay, you've talked about enthalpy, and I kind of get that, but why refer to it as H? Doesn't it start with the letter E?
It does start with the letter E.
It does if I spelled it correctly, but H infers heat, and voila, we thermodynamically have decided to use it throughout the industry. In refrigeration, the pressure enthalpy diagram, or simply pH diagram, depicts thermodynamic properties of a specific refrigerant at given points in a refrigeration system and allows analysis of the refrigeration cycle for that particular substance that's being circulated. Recall that enthalpy is a measure of energy in a thermodynamic system. In refrigeration, enthalpy is a measure of heat energy expressed in BTUs per pound. As the name pressure enthalpy diagram implies, the vertical axis lists the refrigerant's pressure, typically in PSI-A, and the horizontal axis lists its enthalpy in BTUs per pound. On the left side of the saturation dome, I guess that would be over here, right, John?
That's correct.
The
left side.
That's this left.
Yes,
the refrigerant reaches the bubble point as it crosses into the subcooled liquid zone. On the right side of the saturation dome, the refrigerant reaches the dew point as it crosses the superheated vapor zone. That would be superheated vapor boundary.
Right.
For these reasons, bubble point up here is used to calculate subcooling, and dew point is used to calculate superheat. And that'll make more sense as we go along here.
That's correct.
There are numerous other refrigerant thermodynamic properties depicted on a typical pH diagram. Here's a typical pH diagram with a whole bunch of extra lines on it. We're going to explain what they mean in greater detail. Here we go. Bear with us. On a pH diagram, the lines of constant pressure run in a horizontal direction across the chart. Constant temperature lines generally run in a nearly vertical direction in the subcooled liquid region and superheated vapor portions of the chart. Within the saturation dome, the constant temperature lines run in a horizontal direction, illustrating the saturation temperature of a single component refrigerant being constant at a given pressure. Entropy, untie my tongue.
Easy for you to say.
Easy for me to say. Entropy, which we haven't discussed yet, the mathematical relationship between heat and temperature, is represented by lines extending in a diagonal direction toward the top right of the saturated vapor line. I guess that would be this.
That would be those.
Entropy relates to the availability of energy. The presence of these lines on the chart is relevant in that vapor compression, this is important, in an ideal refrigeration cycle occurs at constant entropy. The horizontal axis of the chart shows the heat content, or enthalpy, which we've talked at length about now so far, of the refrigerant, in this case, BTUs per pound. On a pH diagram, as you've seen there, the trapezoidal box drawn over the pressure enthalpy graph, as you can see here, represents the refrigeration cycle. The diagonal line rising toward the top right from the bottom right of the box represents the vapor compression cycle. That's right here. The horizontal line across the top of the box represents high temperature vapor being first desuperheated and then condensed as the refrigerant crosses the dew point, back over here, are the saturated vapor line, and continues through the saturation dome. Heat is removed, and finally the liquid becomes subcooled in this area. As it crosses the bubble point are the saturated liquid line. The vertical drop that you see here on the left side of the box represents the drop in pressure, which occurs through the metering device, feeding the low temperature liquid and vapor mixture into the evaporator. This is a constant enthalpy process. Oh gosh, John, would that be adiabatic?
It could be
Would that
called
be
adiabatic.
Would that be isenthalpic?
Isenthalpic is another valid word.
But John, man, we got to be careful here because we promised, you know, there may be Sporlan accountants or HR managers listening into us, and we promised not to use any big words.
Oh, that's true. We did. Sorry about that.
The horizontal line moving toward the right across the bottom of the box represents the mixture of liquid and vapor boiling into a vapor as the refrigerant approaches the dew point over here and finally becomes superheated as it crosses the saturated vapor line before re-entering the compression process to complete the cycle and then start all over again. And there's that compression process. There is the condensation process. Here's the drop in enthalpy, then here's the evaporator. The four sides of the trapezoid represents the four basic components in a vapor compression cycle. The compressor, where the pressure and temperature of the refrigerant vapor are increased to form the high side of the system, as you see over here. The condenser, where the heat is rejected from the refrigerant to the ambient or reclaimed as the refrigerant condenses back to a liquid. The expansion device, right here, where the refrigerant undergoes the drop in pressure back down to the low side of the system with an accompanying drop in temperature as well. The evaporator, where the heat removal process begins while the refrigerant changes state to a vapor and the low temperature saturated refrigerant liquid boils all while removing heat from whatever you want to cool or whatever you want to chill or freeze, only to re-enter the compressor and start all over. In addition to these four primary components, the system includes the refrigerant, of course, the lubricant, and all the interconnecting tubing and piping. This is the most widely used type of mechanical refrigeration system in the world today. There are many other methods of creating a cooling effect, but this does preserve food for future use and keeps us cool and dry in places that aren't. Each transferred from a low temperature thing or place to make that thing or place cool, cold, or frozen. That heat is then transferred to a high temperature environment and either reclaimed or discarded. You know, this is no easy task, but it consumes energy to make it happen. You know, you've got to put some electrical energy or some other energy into that compressor to make that happen. But these systems are scalable, they're efficient, they're historically reliable, and they're simply everywhere in our modern world. I'd hate to do without them, right, John?
Yeah, if we didn't have them, good luck trying to live in Austin, Dallas, Phoenix, Vegas,
Well, you might get by staying cool with a swamp cooler in those dry environments in lieu of traditional air conditioning, but how do you keep food nice and fresh and preserved?
Great question.
Yeah, so simply, the vapor compression refrigeration cycle, don't leave home without it. We're just about to wrap this up. If you have any questions, let us know. John, do we have any questions that you've seen come up? You can type them into the Q&A window. Eventually, you'll be able to look at this and view it on Facebook and YouTube. You can also type questions in the comments in Facebook Live, I do believe. We have any questions? Is anybody still out there?
I think we're
in good shape.
Good shape right now. I think we have a couple of questions we'll answer otherwise, but yeah.
Okay, well, just to let you know, we're always here to assist you with your AC and refrigerant flow control needs. You can reach us by calling the general number for Sporlan HQ. That's 636-239-1111. That number will provide options to get you to customer service or tech support. You can also dial tech support directly with 636-392-3906, or you can shoot them an email at svdtechsupport@parker.com. We're always here 24/7 to help you by going to sporlan.com. You can get product literature. You can access Virtual Engineer. By the way, I think we may be considering doing a future webinar on Virtual Engineer. That's Sporlan's product selection software program. And of course, you can find a whole lot more. You can view an encore performance of this webinar on Facebook or YouTube, and it will appear on our Facebook page first and on the YouTube channel a little later. Eventually, it'll be out there for you to view again and again or to see for the first time. Again, here's that shameless promotion for the next webinar on October the 22nd. We will follow the schedule of the original supermarket series, and we'll conclude our discussion on methods of temperature control by elaborating on the electric expansion valve and how it can be used to control discharge air temperature, and as a surprise, also superheat.
Superheat.
Yeah.
Ooh,
as opposed to Superman. I'm going to say this concludes our webinar on What is Refrigeration Part 2, Chill Skills Training Module. Please join us the next time.
Please do.